In this video, we are going to look at basically the law of conservation of energy as it applies to two types of energy only. It applies to lots, but we're just going to look at its relationship between potential energy and kinetic energy. Okay, maybe I should write those that other way that I said I like to write them. So energy potential and energy kinetic. And then we'll solve some problems related to using that law of conservation of energy, just using those two types of energy. So first, the law. In an isolated system, concealed sort of system, the energy in the system is constant. In other words, it doesn't change. In this system, then, energy is not created or destroyed, but it can be converted from one form to another, say from potential energy to kinetic energy, or back and forth. And those are the two that we're going to look at. So basically, say if I have 10 units of energy altogether, I could have maybe 5 of them as potential energy and 5 as kinetic energy. Or I could have 8 potential and 2 kinetic. But the sum total of all of those energies has to remain constant. That's sort of what they're saying with the law of conservation of energy. So let's look at it in relation to a question. So here I've got a ball. So right there I've lifted the ball up. Don't worry about what I did to get it there, but we're saying I have a ball that's 10 meters in the air. And so if I wanted to, I could figure out what the potential energy of that ball is, simply by taking energy potential is equal to the mass, 1 kilogram, times gravity is 9.8, times the height of 10. So 1 times 9.8 times 10 comes out to 98. Now, if the ball isn't moving, let's check out its kinetic energy. So the energy kinetic is equal to a half times the mass is 1 kilogram. Maybe I'll put things in brackets. Times the velocity is 0 squared. So if the velocity is 0, then when you multiply all this together, you get 0. So the kinetic energy, if the ball is not moving, of course, is 0. And if you look at this, you can see that the sum of the two energies, oh, here I said to use gravity is 10. We're using 9.8. The sum of those two energies is equal to 98. So that's sort of the total. So it makes sense, hopefully, that if I drop the ball down to half, so if I drop it down to 5 meters, so the whole distance is 10, so now I'm at 5 meters, it makes sense that this would be half. So the potential energy would be equal to half of that, or 49. Now, if the potential is 49, then the kinetic energy has to make up the difference to get to 98, which is another 49. At any point along the whole thing, the sum of the two energies, potential and kinetic, according to the law of conservation of energy, must be constant. So they're at 98. Now, if I take the ball, finally, and take it and put it right down on the ground level, then the potential energy is right on the bottom, so the potential energy is going to be 0. There's no height. The height is 0 now, so 0 times anything is going to be 0. But the kinetic energy, as the ball is about to hit the ground, will be equal to 98. So again, the sum of all of those comes out to being equal to 98. Now you can use that in some questions sort of in an interesting way. We'll try a couple and then we'll look at a different kind of route for that ball to go down. But this law of conservation of energy stays true. So here we've got a question. 2.4 kilogram ball. So here's a ball, and it's 2.4 kilograms. And it's raised to a height of 3 meters. So the height from there down to level is 3.0 meters. What is its potential energy? Okay, I can figure that out. Energy potential, mass times gravity times height. Its mass is 2.4 kilograms. Its gravity is 9.8 meters per second squared. And its height is 3 meters, or 3.0 meters. Okay, So if I multiply all those together, what do I come up to? 2.4 times gravity times 3.0 equals 70.56. 70.56. So that's the potential energy of that ball up there 3 meters high. Now the question now says the ball is dropped, and just as it hits the ground, so I take that same ball and I'm dropping it. Okay, so it drops, and just as it hits the ground, right there, the question is, what will it be its potential energy? So if it hits the ground, if it's about to hit the ground where the height is equal to 0, if you plug a 0 in for there, the whole thing comes out to 0. So the potential energy at, we'll put 0 here, so that's at the bottom, is equal to mass, 2.4, gravity is 9.8, but the height now is 0, so the whole thing comes out to be 0. So the question then is, well, where did this joules, where did that energy go? Of course it went into kinetic energy. So right here at the bottom, the energy of kinetic energy at the bottom will be, we don't know how fast it's going, but I know how much energy it's going to have. It's going to have 70.56 joules of energy. And I know that because law of conservation of energy. So if it had 70.56 there, as it comes down, it loses potential energy but gains kinetic energy. And just as it hits where the height is 0, all of that potential energy will have been transferred into kinetic energy. Okay, so that potential at the top is equal to this kinetic energy as it hits at the bottom. Oh, now they say halfway down, what would be the kinetic energy? That's a good question. So that's first question. Second question. So the third question, what if the ball's halfway down right there? So that would be at 1.5 meters. Well, it follows that if I've gone halfway down, that my kinetic energy will be half as much as it was at the top. So for that third question, my potential energy is equal to the mass, 2.4 still, times gravity, 9.8 still, times 1.5, because that's half of the height. And if you multiply that, it should give you 35.28. I haven't worried too much about sig figs here, but anyway, 35.28 will be the amount of energy halfway down potential. Now, it should be exactly the same for kinetic energy because it's halfway down. All right, let's explore this question maybe in a slightly different way. So we've got 2.4. Here's the question that I wanted to do. How fast will the ball be going halfway? Or how fast will the ball be going when it hits the ground? Well, with kinetic energy, I have this formula, half mv squared. If I know what the kinetic energy is, and I know what the mass is, I should be able to figure out the volume. And we did that in a previous video. So let me just manipulate the formula. It'll be 2 times the kinetic energy divided by the mass. That'll give me the velocity squared. So 2.4 kilogram. Oh, now that's the same question as one we just did. So let's just go and cheat and figure out what the kinetic energy is halfway down. So here was potential at the top, potential at the bottom, kinetic at the bottom, and then right here, this is the one that was halfway down. So 35.28. So kinetic energy is 2.58. Okay, so we'll solve for V. 2 times the kinetic energy, what was that again? Kinetic energy halfway down is 35.28. So 35.28 divided by the mass of the object, 2.4, is equal to V squared. Now, let's multiply that out. So 2 times 35.28 divided by 2.4 equals 29.4. So this is 29.4. Yes, 29.4 is equal to v squared. The units for this would be m squared. And then if you square root that, 29.4 square root, whoops, uh-oh, 29.4, boy, I need to learn how to use a calculator. 29.4, there we go, about 5.4. So the velocity would be equal to 5.4 meters per second. Oh, this up here should have been meters squared per second squared. And then you take the square root of each of those. So halfway down will be the kinetic and potential energy. We'd solve that on the other page. How fast will it be going at halfway? 5.4 meters per second. How fast will the ball be going when the ball hits the ground? That's an interesting question. Would you just double that? Let's figure out and see if doubling actually works. I don't think so, but let's check. What we need to do is figure out what's the kinetic energy as the ball hits the ground. So the potential energy of the ball at the top is equal to the kinetic energy of the ball as it hits the ground. So 70.56. So let's go down here. Okay, so since potential energy at the top is equal to the kinetic energy at the bottom as it hits the ground, and it was 70.56 joules. So to figure out the velocity, I can use the same formula because the mass of the object of the ball didn't change, so I can use the same one. So kinetic energy is equal to a half mv squared. So 2 times kinetic energy divided by the mass is equal to velocity squared. Okay, so the kinetic energy was 70.56. So 2 times 70.56 divided by the mass, which was 2.4, is equal to velocity squared. So now I'll do my calculator here. 2 times 70.56 divided by 2.4 equals 58.8, and then I need to take the square root of that. Whoops. I lost it. Okay, 2 times 70.56 divided 2.4 equals, and then square root of that number is 7.67, call it. So velocity equals 7.67 meters per second. Let's just check if our doubling thing worked or not. 5.4 halfway down. If you double that, that's over 10. But in our case, it didn't get that high. So you can't just double the velocity as you might think that you could. So the velocity as it hits the ground will be 7.67 meters per second. Hopefully you're getting familiar now with using that law of conservation of energy and the interaction between potential energy and kinetic energy. Here's another question. And for this question, just for simplicity, I'm going to use gravity is equal to 10 meters per second squared. Usually I like 9.81, but for just simplicity, we'll use 10. Multiplying by 10 is easier than multiplying by 9.8. Okay, if I have a ball, and if it's on a frictionless surface, that would be an important word to use here, if it's on a frictionless surface. Okay, and you roll this ball down in this kind of a pattern. If you're looking at the law of conservation of energy, it really doesn't matter if you take that ball and bring it down halfway, or if you take that ball down and put it on a path where it winds up to be halfway. So it doesn't matter if you put it on this path to get there, or if you take the ball and just drop it to halfway like that. The potential and kinetic energy will be the same for each one of those. So for example, if I wanted to know what the potential energy of that ball is right there. So energy potential is equal to mass times gravity times height. Mass is 1, gravity we're calling 10, the height is 10. So the ball has 100 joules of potential energy right there. So if I drop that ball to halfway, it would have half that potential energy, or 50, regardless of whether I put it there or if I let it, come down on this path and come right to there. If its height is 5, its potential energy is half of that, because that's half of 10. Now, I guess my question is, how fast will it be going at 5? Or how fast will it be going at 3? You could use the same kind of logic for each one of those. So if I wanted to know how fast it's going at 5, then I have to figure out what the kinetic energy is at that point. Well, if potential energy at the top is 100, potential energy halfway down then would be 50. That would be potential energy. The kinetic energy, law of conservation of energy, have to add up to 100. The kinetic energy also has to be 50. So if I again use that formula, kinetic energy is half mv squared, or 2 times the kinetic energy divided by the mass is equal to v squared, and then take the square root of that. 2 times the kinetic energy at half is 50, divided by the mass is 1, is equal to v squared. 2 times 50 is 100, divided by 1 is 100. Square root of 100 is 10. So the velocity of that ball right there at 5 meters, it'll be going 10 meters per second. And it'll be going 10 meters per second there, or it'll be going 10 meters per second right there too, if that's at the half point. And you could figure out how fast it would be going at 3 as well, simply by figuring out how much kinetic or how much potential energy it would have at 3. And at 3, just by doing a ratio proportion there, 3 would seem to be 30 joules of energy. So if it has 30 joules of potential energy at this point, then the kinetic energy would have to be the difference between 30 and 100, or 70. And then you could take the 70, plug it into the formula, and figure out the velocity. So in this video, we have looked at something called the law of conservation of energy. And we've looked at that in relation to potential energy and, well, not equals, potential energy and kinetic energy. Okay, hopefully that helps. Try some questions.